My name is John Hughes. I've been working with functional programming for all of my career. I got into it very early on. I wrote one or two of the seminal papers, Why Functional Programming Matters.
Yep.
One of my best-known papers. 15 years ago, I got interested in testing, and Kuhn Klassen and I came up with Quickcheck, which has been quite influential. I started my own company with Thomas Arts about 10 years ago. Since then, I've been doing a lot of work with Quickcheck in particular, having a lot of fun seeing the ideas that I got excited about 30 years ago actually paying off, being put into practice. And nowadays I do a lot of speaking at conferences like this, trying to help those ideas spread.
I've read the paper, but for those who are watching who haven't, why does functional programming actually matter?
So what that paper is about is ways of composing programs. If you think of old programming languages like Fortran or C, whatever, you can put programs together in certain ways, but functional languages traditionally have given you other ways of putting programs together. So higher order functions, when you pass functions as first class citizens, you can pass them as parameters. They let you define things like maps and folds that then let you express, you have a kind of skeleton that you can instantiate by passing in a first class function, and you can build a lot of useful functionality just by reusing higher order functions. So that gives you a kind of reuse of code that you don't have if you don't have functions as first class citizens. And lazy evaluation is kind of similar because it lets you separate the body of a loop that is producing a sequence of values with a termination condition. You can put those in two separate functions and then compose them together. And when you can tease apart the termination condition and the loop body, then you can reuse those in different ways. And the idea of the paper is really, if you look at the ways that you can compose programs, think of those as glue. When you have new kinds of glue, that means you can build up your program in a new way. But if you can build up your solution in a new way, you can also break up your problem in a new way. And so it's kind of modularity as a way of solving problems. New kinds of problem decomposition can let you break problems down more easily and write much more concise code.
So what type of problems would functional programming be better at than, let's say, imperative C programming or declarative programming like SQL? Is there like a subset of problems that functional programming is really good at?
I think it's easier to ask, is there a subset of problems that it's really bad at? Functional programming doesn't usually give you fine control over your use of memory. If you're writing the kind of code where you really need to think about the layout of data in memory, think about how the cache is going to work, and really optimize that very, very hard, then a functional language is probably going to make your job more difficult. I think that's a rather special kind of code. So just as, when I was a young computer scientist, people still wrote assembly language. But for the most part, it would be, the tiny, really performance critical parts that you might write in assembly, and you could use high-level languages for most things. So I think the situation is kind of similar with functional programming, that yes, there are really performance critical places or really memory critical places where you need the fine control that an imperative programming language gives you. But the rest of the time, life is too short.
So I know that you had actually spent some time in the Haskell world, and now is most of your time spent in the Erlang world?
I'm still dividing my time, but I'm now spending more than half my time at our company, and our company is working with Erlang. So naturally that's occupying more and more of my attention. But I was involved with Haskell right from the start. I was on the Haskell design committee. I've used it very, very much over the years, of course.
That's fantastic. What is the startup that you're actually working on now? I know that you actually do testing. Can you actually talk about that a little bit?
So it's based on a testing tool called Quickcheck that came out of research that I was doing at the university around about 2000. And the idea behind Quickcheck is that instead of writing automated tests of the kind that everybody is familiar with, where you're really focused on thinking, well, what cases do I want to test? And you're less focused on how do I know whether or not the test passed. The idea with Quickcheck is that instead we let Quickcheck generate the test cases, and what we write instead is a general property that should always be true. So for me, when I first started thinking about this, it was like taking ideas of formal specifications, formal methods, how do you define what correct behavior is, and turning that into tests. And I originally did it just for fun. This is my most influential research, apart from why functional programming matters, and actually is much closer than you might think, if you look at the number of citations.
Interesting.
And it happened because I've been working very hard on something very important for a long time. Can't remember at all what it was. And then I was done. I had nothing to do for a week or so. And I thought, what can I do that would just be fun? And I came up with this idea that wouldn't it be great if you could just write down a property and then instead of having to, test by all the hard work of thinking up cases, just have it happen by magic. I thought that would be cool.
That'd be brilliant.
And Kuhn Klassen stuck his head in my office door one day. He said, "What you doing?" I said, "Oh, look, I've had this little idea." And I showed him what I was doing. And then next day he came in and he'd made a much better implementation. But so I played with that, and he hadn't thought of everything either. So I had some more things. So the next day I showed him my one. And that kind of went backwards and forwards. It took us about a week to make the first version.
Wow.
And it was purely for fun. I didn't realise, actually, for several years, not until our funding agency pointed it out, that it could really be useful. But now I know it can, of course. So that was where the first idea came from. When I give talks, I often start by asking the whole room, who here really, really loves testing? You should see the number of hands go up. It's very, very few, and it's quite often the people I know are using Quickcheck.
Interesting.
So this is part of the idea. I mean, you were saying laziness is a good thing in software development. The whole point of Quickcheck is to make testing. Let's be lazy about testing. Who wants to do the tedious stuff? Thinking, okay, I should take 0, I should take 1, perhaps I should take -1. Again, life is too short for that. So instead, we let Quickcheck generate the tests, and we focus on the fun part of figuring out, how can I tell that this test has passed? What should my code really be doing? We turn testing into development, and we all enjoy development, right? So a big part of it is that it makes testing fun. So really fun.
Does it actually generate the tests for you by inspecting the code that you've written?
So yes, it generates tests for you. You have a lot of fine control over that. So a part of what you do is you write. Actually, what you're doing is you're writing a test data generator. But we have an API that makes that very easy to do. So instead of yourself coming up with hundreds of tests, or dozens of tests maybe, you write the test data generator that will come up with all of the tests for you. And you still have to think about, how do I want to test this? What kind of test data do I want? But then instead of thinking up 4 examples, you write your generator and you say, okay, I want to prioritize this kind of data half the time, that kind of data quarter of the time, so on. Got very fine control. And then what Quickcheck does is it generates random tests according to your generator. We run the tests. When a test fails, usually the test case we've generated, it has 1 or 2 important features that actually caused the failure, and a lot of random rubbish that just ended up in there. Because we're trying all kinds of stuff in the hope of finding something that fails. But when a test fails, a lot of it is irrelevant. The other thing that Quickcheck does, which is really, really important, is that it takes that failed test, full of noise, and it distills it down by doing just what you would do if you were debugging a failure from production. You'd have a long sequence of things that cause an error, and you go through saying, well, can I take that away? Can I take this away? Can I take that away? So because we know for each test case, we can find out, is this a passing test or a failing test? We can actually do that search for you, and we end up with a minimal example, a little test case in which every part of the test case matters for the failure. And that's what we then report to the users. We call that shrinking. When you get that shrunk test case, when you know that if this number is 1 and not 0, it's because that matters. Then diagnosing what went wrong is usually really, really easy.
You tell it more or less what you want to test for. The program generates a bunch of random tests within the parameters that you actually have set. When it breaks, it actually starts removing some of the randomness and actually tries to distill it down to what actually broke the app, and that should be something that's generally something very important that actually mattered. Is that correct?
Yes, it's generally a small example
Yep.
that demonstrates why you have a bug in your code. And usually, no matter what random test first fails, you end up with the same small example. So Quickcheck is very stubborn at that point. It says basically, fix this, and then you can go on.
How many languages does this actually work for, and what types of software can you actually use Quickcheck for?
So the first version was made by me and Kuhn in Haskell. That version is used very extensively in the Haskell community. It is the most used Haskell testing tool. So there is a XUnit style tool for Haskell, but that's used maybe about half as much as Quickcheck. And I discovered the other day that if you look on Hackage, which is the Haskell database of open source packages, Quickcheck is, I think, the 10th most used package in terms of dependencies. Which, when you consider that in the first 9, you've got things like the language-based libraries and file IO and stuff like that.
Wow.
Then that's a pretty good position to be in.
That's fantastic.
So that's been really successful. When we started Qlik, then we based that on an Erlang version, and we did that for pragmatic reasons. That we had Ericsson as our first customer, and Ericsson were using Erlang, so it made sense. But I think it was actually, it turned out to be a very successful choice. I was a little bit concerned when we started on that we didn't have the type system that Haskell has, and so I expected that we would be able to make a version that would be, good but not quite as good as the Haskell version. But I think that was not the case.
Really?
Yeah, it turns out that for a lot of the code that we write in Quickcheck, actually the type checker gets in the way. I never expected to say that. But actually it does. So we're able to provide a nicer interface for writing the Quickcheck specifications, thanks to the fact that we don't have a type checker. On the other hand, it means that, of course, when we make type errors in our code, instead of having the type checker say, there's a problem, we have to find those errors by testing. But wait a minute.
If only we had a tool that helped us do that.
Exactly. So all of my code, it's tested so thoroughly, so soon after I write it, that if I make a type error, I find it maybe not like that, but like that.
Wow.
And so the disadvantage of not having the type checker, it's minimized for the kind of code that we're writing. And the advantage is, outweighs that.
So would you actually run Quickcheck at compile time? When is the Quickcheck actually run in the process of developing the code? For instance, I've actually lived a bunch of time. Most of my life is actually spent in the interpreted language space. Python, Ruby, PowerShell, that sort of world. So if you have Quickcheck for Python, and I read that you do, at what point is my code actually run through Quickcheck, or do I run? How does that actually work?
I should say we don't have Quickcheck for Python,
Okay.
but because the Haskell version is open source, and
Perfect.
the idea has been very inspiring for other people, and so there are many Quickcheck clones, tools inspired by our original work. And they vary a lot, but the chances are, for many programming languages, you're quite likely to find a version of Quickcheck or something inspired by Quickcheck. And then how good it is, that varies a lot, but the idea has been widely emulated. But the Python thing will be one of those.
No, that actually makes perfect sense. And so Is your core business selling a Quickcheck product, or is it the open source plus consulting model, or how is the business model around the company that you founded?
So our product is not open source. We do sell licenses,
Yep.
but what we've found over the years is that it does demand a different way of thinking about testing. So just putting the product in people's hands is usually not enough. Right? So the services that go around the product are as or more important than the product itself.
So it's product plus services.
Product plus services.
How has it been going from the academy to the enterprise?
Wonderful.
Really?
Yes. So I think it's partly everybody needs a change at some point. So when I started Cubic, I'd been a professor for 20 years.
Wow.
Of course, working in the academia and doing research is a whole lot of fun.
Yeah.
But nevertheless, it's a little bit
Of a grind.
the same. So some people go on sabbatical.
Sure.
I couldn't do that. We have a handicapped son and it just wasn't possible. But instead, I started a company. I entered a whole new world. And for me, that was really very, very stimulating. I'll tell you something else. In academia, when you have a good idea, then you have the idea. You think, wow, that's great. So you do the work. You write a paper about it. That takes a long time.
Yep.
You send it in to a conference normally. And then you wait. You wait several months. And after a few months, you get reports from the referees. And they're never as excited about your idea as you were. So sometimes you have a referee that says, yes, this is very nice. But often they say, well, they could have done that better. They could have done this better. I suppose we can take it. So referees' reports are always a bit of a mixed bag. And even, I remember one day when I was a research student, I was in the Tony Hoare's department. And Tony Hoare is one of the really great computer scientists. And one day he was looking a bit miserable. And it turned out it was because he'd just had a paper rejected. This happens to everybody. It's part of working in academia. So you get the referees' reports back, and you make the improvements, and you send in the final version. That takes another few weeks. Then some months later, you go to the conference, and you give the talk. And it's maybe a year after you had the original idea. You give the talk, and if you're lucky, after the talk, some people will come up to you and say, that was really great. But there's this long, long period between when you have the idea and you get the excited about it and when you get the feedback. If you do something good for a customer, they're happy straight away.
Absolutely.
I really love that.
Have you actually had many companies in the United States actually start to use your product? In Europe, where is the sweet spot in terms of your customer base?
Biggest customers have been in Europe, and actually the biggest project that we've done was for Volvo Cars in Gothenburg, which was kind of nice. That's where we're based.
Wow.
So that meant we didn't have to travel
Excellent.
all the time. But we have customers in the US as well. One of our bigger customers is Basher Technologies, actually.
Oh, wow.
The React database.
Yep.
And they have a very, very excellent development team, and we've been working quite closely with them on developing Quickcheck specifications of parts of React.
Tell me about testing software on automobiles.
Yeah, that was really interesting. The problem that Volvo had is that the software in automobiles, there's a lot of it. You've got 50 to 100 processors.
Wow.
And they need all to talk to each other. But you're buying the processors and the software from different suppliers. There are a lot of under-suppliers in the vehicle industry. So when you put the car together, you've got software from many different suppliers. Is it going to work together? To make it work together, the whole vehicle industry has defined a standard called AUTOSAR. And so that specifies a whole lot of stuff, but in particular, the basic software, so-called, which is like the operating system that will run on every processor in the car. So the operating system, it's not the same implementation on each processor, because there's many suppliers of that. But it's standardized, so when you put it together, it'll just work, right? Well, no, it doesn't, of course.
Wow.
You put the car together, you can't even boot it. And for Volvo, that's a big problem, because if two processors won't talk to each other, they don't even know whose fault it is. So they they wanted acceptance tests for the basic software. And we helped them by developing those. And this involved reading 3,000 pages of standards documents.
Oh my God.
And we turned that into 20,000 lines of Quickcheck specifications.
Wow.
We use it to test, in total about 1 million lines of C code. Because all of this stuff, it's low-level C code, of course.
Oh my gosh.
And we found hundreds of problems.
I can imagine. There was a piece from some students at the Washington State University who had actually managed to remotely trigger using some of the wireless sensors on a computer to actually exploit some of the cases, and they were actually able to remotely steer, accelerate, and brake the car. As I read that, I started to read a little bit more about some of the software inside of cars, and my initial inclination was just to run away screaming. Because I'm like, oh my gosh, this is going to be such a nightmare. And especially with the Internet of Things taking more of those characteristics, I think something like what you guys are doing is really, really needed. And thank you for your contributions to computer science. Thank you for writing your functional programming paper. I enjoyed it very much, and it's been very influential in my growth as a software engineer. And thanks for the time of speaking with us. Thank you very much, sir.